Hello viewers, my name is Geoffrey Omondi. We had a class of probability the last time and we talked about combined events. Now we had agreed earlier that there are mutually exclusive combined events and we still also have what we call independent events. Now today I want us to continue and still look at the events. Now, we agreed in the first instance that when we are dealing with the events, the most important thing is to be able to come up with what we call a sample space, which was to tell us actually the total number of expected outcomes. Now, in today's class, I want us to look at another way in which we can come up with what we call a sample space. Now, that other way we are talking of today is what we are calling tree diagram. So in this class, I want us to actually look at what we call the tree diagram. So we're talking of probability, that is our topic. And we are saying that we can have a sample space. And the sample space, we had agreed we can represent it first of all by using columns or rectangles that can show us the total number of outcomes, but we can also use what we are calling a tree diagram. So today I want us to look at what we call a tree diagram. Now, consider, I want us to start from that point. Consider two coins tossed one after the other. So I want us to come up with a sample space of two coins tossed one after the other. So we can create this way and say we have the first coin. And at the same time, we can say that we have the second coin. Now, the first coin can give us only two responses, either a head or a tail. The second coin can only give us only two possible outcomes, either a head or a tail. So working with this, we can draw a sample space this way and say that the first coin can give us a head, followed by the second coin also giving us a head, or the first coin can give us a tail, followed by the second tossing giving us a head, or the first toss of the coin can give us a head, followed by the second coin or the second toss giving us a tail, or the first toss, let me just say the first coin toss so that most of us can visualize. The first coin toss can still give us a tail, and the second toss give us also a tail. So looking at this, viewers, we can therefore say that our possible outcomes are now these. We can have head for the first, followed by head again, or we can have tail followed by head, or we can have head followed by tail, or we can have tail followed by tail. So this is what we actually refer to as a sample space, or what we also call, if we want, a probability space. So we are talking of a sample space or a probability space. We can get it this way. But we are saying that we can also get this by using another method. We can also get this by using another method, which we are also referring to as the tree diagram. So let's consider the same statement, two coins tossed one after the other. So looking at that, two coins tossed one after the other, we can look at that way and say that in the first toss, there can be a head, or a tail like that. Second toss, if you had a head in the first toss, you can still get a head or a tail. But in your first toss, probably you had a tail. So if you had a tail in the first toss, you can still have a head in the second toss or a tail in the second toss. So this will be first toss, second toss. So this will be first toss, this will be second toss. So those are the tosses. Now, looking at this, we can now have several outcomes. Let's look at our outcomes. So our outcomes, first of all, there can be either a head and a head, which will be HH, or another possible outcome, if we had a head in the first place, we can follow it by a tail. So that will be head, tail. Or if we had a tail in the first row, we can now have a tail followed by a head like that. Or we can have a tail followed by a tail. So in that instance, these become our outcomes. Those become our outcomes. So we can therefore say that the possible outcomes, in that case is the first one there, head, head, or followed by head, tail, or followed by tail, head, or followed lastly by tail, tail. So these are our possible outcomes. Now you can see that I've had similar outcomes in both instances. Using outcomes, getting outcomes, using these branches the way I've done. These ones resembling branches, they resemble branch of a tree. This is what we are referring to as a tree diagram. So what I've drawn here is actually the whole of this is what we are referring to as a tree diagram. So this is basically what we are referring to as a tree diagram. Now, I want us to know that tree diagrams are normally very important, especially where we are dealing with more than 2 events or more than 2 attempts. For instance, we would have a problem enumerating this in a table this way if we were talking of a third toss. But when we are talking of a third toss in a tree diagram, actually we can simply add it. So I want us to get an example. Which we can work on and see how it is. I want us to get an example. So the example we are going to work with, we are going to get it from your KLB course book. I want us to get an example from KLB course book. Yes, here is the example. So I want us to get an example. So a coin is tossed 3 times. A coin is tossed 3 times. Draw a diagram to show all the possible outcomes. B, find the probability of getting 1 head, 2 heads and a tail in any order, 2 heads and a tail in any order. 3 2 heads and a tail in that order. 2 heads and a tail in that order. We can clean here so that we can continue. Four, 3 heads. 4, 3 heads. 3 heads. 5, at least 1 head. At least 1 head. 6, no head. No head. So I want us to work on those for now, and we see how it's going to work. So solution. So we are told that the first thing that we're supposed to work on is to draw a tree diagram. So we have to draw that diagram, and it's simple. We'll start by that. So we are told the toss is 3 times. So our first toss will give us only 2 options, either a head or a tail. A head or a tail. Second toss. So second toss, if we had a head, we can still get a head and a tail. But in our second toss, it's also possible that the first toss was a tail. So we can still get a head or a tail in the second toss. The third toss, therefore, so this is third toss, we can still get a head and a tail. A head and a tail. A head and a tail. A head and a tail, like that. Now, I want to explain this because it is very important. When you're dealing with this, I want you to know that this is the first toss. In the first toss, our sample space only has 2 things. Either we are getting a head or a tail. In our second toss, we are now working from 2 bases. In the second toss, we are agreeing that in the first instance, probably we had a head. But if we had a head, we can still have a head or a tail. And it doesn't depend on what we had in the first instance. In other words, if we had a head in the first instance and we have a head now, we can go ahead and say that we now have 2 heads. Still, we can have a tail in the second throw, but at the same time we had a head in the first throw. So I want us to know that as we move on, we keep on branching. We keep on branching such that every other thing that comes from this first head, let me just show, though we will still erase this so that you are able to see. You have to see that all these things that are under this dotted line actually happen, and they are not dependent on the first head happening, but they are the descendants of the first head, such that from this we can only have head, tail, head if we actually had a head in the first instance. We can still have a head, head, tail only if our first throw was a head. So I want us to make it very clear, therefore, that as we move, our options keep on increasing, such that I want to illustrate simply from a simple family tree. A simple family tree. This is just illustration. If in your family there is a grandfather, or let's say a father, So father can give birth to two children, a boy and a girl. Still, a boy can give birth to two children, a boy and a girl. And the girl can also give birth to two children, a boy and a girl. Now, the boy of the boy here can still give birth to two children, a boy and a girl, and this girl can still have a boy and a girl, and this one can still have a boy and a girl, and this one also a boy and a girl. Now, when you look at all this, if we were, for example, to pick this girl here, although this girl has so many cousins, but how many generations are we talking of? 1, 2, 3. This is a grandchild to the father. Just like if we were to pick this boy here. In other words, whether this boy is a boy or a girl does not depend on anything. It can be a boy or a girl. But at the same time, is only existing. We can only talk of a boy, boy, boy in this family tree if the first grandfather here was a boy. So you are able to see, in this case, we can be able to talk of the first. Like that. We can be able to talk of the second generation like that. We can also be able to talk of the third generation like that. So we are talking of progressive. So if these were coins, this would be our first toss, our second toss, our third toss. So in this instance, you can see we have our first toss, our second toss, and our third toss. So we were using that to illustrate, but I want you to see, we are talking of something like this. The more we continue moving, the more our sample space and the chances increase, the more our probabilities increase. So I want us to continue in that spirit. Let me clean this. Let me clean that way so we can continue. So having worked with this, we can now write here our outcomes. So our outcomes. So this is the sample space actually we are talking about, outcomes. So the first outcome can be, you will have ahead, ahead, and ahead in that order. So head, head, head. So I want you to notice that if you throw the coin 3 times and you have ahead and ahead and ahead, it means that you cannot have any other combination. All your responses are heads. Or another outcome possibility can be the first throw being ahead, the second toss being ahead. I want us to see how we are moving ahead, ahead, and a tail. The third one being a tail. Or we can have a head, a tail, a head. That will be head, tail, head. Or we can have head, tail, tail. So that is head, tail, tail. Or we can have tail, head, head. So that will be tail, head, head. Or we can have tail, head, tail. Tail, head, tail. Or we can have tail, 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 head. Tail, tail, head. Or lastly, we can have tail, tail, tail. Tail, tail, tail. So these are the possible outcomes that we can be talking of. These are the possible outcomes that we can be talking of. So I want you to realize immediately that the first question that was required of you was to draw a tree diagram to show all the possible outcomes. Now, normally it is important to write the probabilities in each case. Now, I want us to know that these are independent activities, such that in the first instance, for you to get a head or a tail, the chance is half-half. So the probability there is a half, and the probability is a half. In your second throw, if you are throwing a coin, there's no relationship with the first throw. So probability remains to be a half, 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 and a half. So all the chances are a half, meaning in every instance there is equal chance of getting a head and equal chance of getting a tail. That's why we are saying that half, half. So I want us to move ahead and start finding the second part, number B. So this is our sample space. This is our sample space. Our sample space is HHH, HHT, HTH, HTT, THH, THT, TTH, TTT. So that is our sample space, or what we also call probability space. That is our sample space, or what we also call a probability space. So I want us to go ahead and try to answer the questions that follow. So one head. What is the probability of getting one head? Now, probability of getting one head, we now have to look at our sample space here and see outcomes that only have one head. For instance, in the first outcome here, we have 3 heads, here 2 heads, 2 heads, 1 head. So we need this, we can tick it. We need it because it has 1 head. We have 2 heads, we have 1 head, so we need this as well. We also have 1 head here. These are now 3 tails, so no head. So these are the 3 possible outcomes we are interested in. Those are the 3 possible outcomes we are interested in. So what will we say? In this instance, therefore, we can say that the probability of getting only 1 head, probability of only one head can be given by the probability of head, tail, tail. So that will be head, tail, tail. Or it can be tail, head, tail. Probability of tail, head, tail. Or it can also be given by the probability of tail, tail, head. Probability of tail, tail, head. So those are the 3 probabilities. Now, there's something I want us to remember. For example, if we say head, tail, tail, what it means, we are looking at the probability of head and tail and tail. In other words, it's the probability of head times the probability of tail times the probability of tail, in that order. So probability of head, tail, tail, this one, this is the probability. So this is a half and a half and a half. So that will therefore be given by a half for the head, followed by a half. I'm using times because this is and, followed by a half. Now, you have to know, along a branch, normally multiply. Even if you are having problem remembering that, just know along a branch we are multiplying. Now, or means plus. Or means plus. Probability of tail, head, tail is this one. So tail is a half times head, a half, times tail, a half. Or the third one, the probability of tail, tail, head, this one. So the probability of getting a tail here is a half. And the probability of getting another tail, a half. And the probability of getting a head in this case is a half. So you can work with that way. So you can go ahead and say that a half times a half times a half, this will be 1 times 1 times 1, which is 1 over 2 times 2 times 2, which is 8, plus, now these are similar brackets, so this will be 1 over 8 plus also 1 over 8. We agreed that whenever you are adding and the denominators are similar, simply add the numerator and pick one of the denominator. So in this case we have 8, then 1 plus 1 is 3 out of 8. So 3 out of 8 become the probability of getting only one head. The probability of getting only one head. So the second part, 2 heads and a tail in any order. 2 heads and a tail in any order. So in this instance, you will now say that 2 heads and a tail in any order. So we are looking in a situation where there are 2 heads. So this is one of them. Another 2 heads, we have 2 heads here, yes. Do we have 2 heads here? No. Do we have 2 heads here? Yes. We have a tail and 2 heads. Do we have 2 heads here? No. Do we have 2 heads here? No. And do we have 2 heads here? No. So it's only these 3 instances. Now, so this can therefore be given by probability of head, head, tail, or the probability of can also be given by the probability of tail, head, head. Let's see. The first one was head, head, tail. Yes. Head, tail, head. Head, tail, head. Or we can also talk of probability of tail, head, head. Tail, head, head. So those are the 3 probabilities we can be talking of. So again, we can work on them. Head, head, tail, a half, a half, a half. So that will be a half times a half times a half. Or the probability of head, tail, head, head, tail, head, tail, head. To get head, there will be a half, tail a half again, another head a half. Or the probability of tail, head, head, tail, head, head. They are all a half. So that will be a half times another half times another a half. So in that instance, we will solve this first bracket, which will give us 1 out of 8, or is the same as plus 1 out of 8, or is again the same as plus 1 out of 8, giving us a total of 3 out of 8. So that is how we can solve the second part. That is how we can solve the second part. That is 2 heads and a tail in any order. 2 heads and a tail in any order. Now, viewers, because this is our question and our space is running out here, how I wish we could still erase here, because we are still using both of these parts, the equation and the tree diagram, to answer what we are dealing with. So you will allow me to clean here again so that we continue working. Now, meanwhile, it is important that I note that only 1 head was 3 out of 8, and 2 heads and a tail in any order was also 3 out of 8. So those are the answers we've gotten so far. So 2 heads and a tail in that order. So in this instance, we are now restricted. There is some order. In other words, we want 2 heads and a tail, and they must follow each other. So we must have a head, and a tail, and no any other order. So we have to look here and see where we have 2 heads first and then a tail later. Yes, so this will become the head, and then followed by a tail. So that will be the third one. So we will be looking at the probability of head, tail, like that. So looking at that, head, the first head, the probability is a half, and we have to get a head again. The probability is a half, and we have to get a tail, which is also a half. So working on this, we can get 1 times 1 times 1, which is 1, over 2 times 2 times 2, which is 8. So therefore, the probability of head, tail is actually 1 out of 8. So we can go ahead and look at 3 heads, probability of 3 heads. Probability of 3 heads. This was number 4. This is now number we are now in number 4. That was number 3. That was number 3. So we have number 4. So number 4 is now 3 heads. 3 heads. In other words, you're looking at probability of head, 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 like that. 3 heads. And when we look at here, there's only one instance where we have 3 heads, which is this. So we'll say the probability of getting a head is a half, probability of getting another head is a half, and probability of getting a third head is a half. So when we multiply this across, we end up with 1 out of 8. 1 out of 8. Finally, we can go ahead and look at least one head. So this will be number 5, at least one head. Now I want us to think. When we say at least one head, we are therefore looking at 1, 2, or 3 heads. Now when we look at this situation, we have them. Head, head, head. So we have at least one head here. The second situation, head, head, tail. So we have at least one head. The third situation, head, tail, head. So we have at least one head. The fourth one, head, tail, tail. We have at least one head. The fifth one, tail, head, head. So we have at least one head. Here there's a head, here there's a head. So there's only one place where we don't have a head, and it is tail, tail, tail. Now, we agreed that these are now mutually exclusive events. In other words, if you have head, 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 you cannot at the same time have head, head, tail. Mutually exclusive outcomes when you look at the general outcomes here. Now, looking at this, therefore, we know that if we add all these probabilities, our answer is 1. Therefore, we can reason, because if we want at least one head, what we will do is we'll get the probability of head, 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 or the probability of head, head, tail, or so we will be adding all these probabilities up to here and fail to add the last one. Now, in that case, therefore, we can therefore decide that if we know that if we were to add everything, our answer is 1, therefore, we can say that at least one head, we can simply say this is 1 minus the probability of tail, 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 which will now be simpler. We'll only take this one, remove from 1, which will give us the total of everything remaining up. So this will be 1 minus tail is a half times another half times another half. So this will be 1 minus, when we work out a half times a half times a half is actually 1 out of 8. Giving us what we call 7 out of 8. So that is how we can work on at least one head. That is how we can work on at least one head. But I want to challenge you. Challenge. Can you use the alternative? Use alternative way of adding all the other outcomes except tail, tail, tail. So I'm giving you that challenge. Can you try adding these ones and see if you'll end up with the same probability? And don't add tail, 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 so that we see if we end up with the same probability. Lastly, no head. The probability of no head. Now, when you look at that, the probability of no head means we have in all the 3 instances, we have tails. So it therefore means we are looking at the probability of tail, tail, tail. So the probability of no head is therefore the same as the probability of tail, 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 which can be given by a half times a half times a half, giving us 1 over 8. So that is how we can work on that when we are looking at the probabilities. Now, you see, when you're dealing with tree diagrams, viewers, it is important that you do a lot of practice. Now, these questions can be long, and therefore, normally it's important that when we leave an assignment behind, you make sure that you attempt and then you look at the comment section just below this video and put your comment there by asking questions so that we can respond in good time and so that it can help you. Otherwise, I want to tell you that questions like this normally attract a lot of points in exam, 10 points to be precise, questions like this, and therefore it's very important to be keen with them. Otherwise, I want to leave an assignment behind that you will attempt. So the assignment is this. Assignment is this. Exercise, this is KLB. KLB. So this is the assignment. KLB exercise 13.4. I want to leave number 1, number 2, number 3, number 4, number 5, and number 6. So this is the last part actually of this topic, but we will continue to do further examples in the next class. My name is Geoffrey Omondi. See you in the next class.